point of translation is to finish the synthesis of the protein by reading the mRNA codons to build the peptide chain. One mRNA codon, or 3 nucleotides, represents one amino acid. The tRNA is what brings the amino acid to the ribosome. The anticodon must pair to the codon to ensure that the right amino acid is being dropped off. Kind of like when you drop off your kid at daycare, they check to see if your kid is on the list, because if they aren't, that would be one more headache for the daycare to deal with. We will now take a quick overview of the wonderful process that is making proteins.
Begin protein synthesis when the 30S ribosomal subunit meets the mRNA. However, in order for the 30S ribosome to know it is binding to an mRNA, it looks for a particular consensus sequence known as the Shine-Dalgarno sequence. It's like looking for a friend in a crowd of people. You are looking for something that confirms that they are in fact your friend, like their face. Once the 30S ribosomal subunit meets the Shine-Dalgarno sequence, they bind together.
Before the party can really get started, the small subunit must head to the party location or to the first codon in the sequence. That codon would be the AUG start codon or the methionine codon. It needs to position itself here so the subunit can start the chain in the right place.
Next, initiation factors join the party to help guide the process in starting protein translation. The main party animal is initiation factor 2 with GTP, because it brings the very first aminoacyl tRNA to the small subunit and mRNA. After securing the goods at the AUG start codon, the 50S ribosomal subunit comes in to get the party started. IF2 will hydrolyze GTP in order for the 50S subunit to join the 30S and form the ribosome. IF2 leaves with GDP since it was only the Uber driver for the aminoacyl tRNA. Now that the players are in place, the party starts and protein synthesis can finally begin.
Elongation is the process of adding amino acids to a growing chain of polypeptides. It's like making a conga line, except the conga line is very particular on who joins in and where they join in. So in a sense, it's a very pretentious conga line. We then begin elongation when an EF2 with GTP brings an aminoacyl tRNA to the A site. Like a claw machine, EF2 just picks one at a random to bring. No thoughts, head empty, just grab and go.
Since EF2 is the double checker as well, it will hydrolyze GTP to let the ribosome know that the proper aminoacyl tRNA is in place and will leave to go grab another one. If the pairing is incorrect, then EF2 takes the wrong aminoacyl tRNA and shamefully leaves. That's okay. Better it shamefully leaves than confidently leave behind the wrong aminoacyl tRNA. Plus, it can try again, since the A site is still waiting for a charged tRNA.
Next, the ribosome catalyzes the transpeptidation, where a peptide bond forms between the N-terminus of the existing peptide chain and the amino acid in the A site. Once the bond forms, the peptide chain is passed on to the tRNA in the A site from the tRNA in the P site, kind of like when your older siblings pass on their chores to you and you can't give them back.
Lastly, translocation begins when EFG arrives with GTP. EFG squeezes itself into the A site and hydrolyzes GTP to cause the mRNA and the ribosome to move over. The process kicks out the uncharged tRNA from the P site to the E site. Here, the uncharged tRNA leaves to go get another amino acid. Kind of like how some parents will kick their unemployed parasitic children out if they don't have anything to contribute.
The tRNA with the peptide chain moves over to the P site. Then EFG leaves, opening the A site for another charged tRNA to come in and add an amino acid. This process repeats itself over and over, with an amino acid being added to the end of a growing chain. This makes the world's smallest conga line, because people aren't microscopic. The process will stop when a stop codon of UAA, UAG, or UGA enters the A site to crash the party.
Think of termination as the IU students that show up at the party and everyone wants to leave. The stop codon arrives at the A site and release factor 1 or 2 arrives. RF1 or 2 binds to the A site and transfers the polypeptide chain to a water molecule, so the polypeptide can leave the ribosome. Then the polypeptide is processed and folded into a protein.
Eventually, backup arrives in the form of RF3 with GTP, like Purdue Pete coming to defend the students from IU. RF3 hydrolyzes GTP, causing RF1 or 2 to leave the ribosome, and the ribosome subunits come apart. Since the IU students ended the party, the ribosomal subunits are recycled and go on to start another party elsewhere.
Join us for an exploration of the microscopic jungle and insight on what happens inside your cells all the time. Purdue students present Safari in the Cell, an introduction to intracellular ecosystems. On this episode, protein synthesis. Sit back, relax, and come explore this tiny, wild world with us.
Today we will be observing initiation of protein synthesis, one of nature's true wonders. Oh, here you can see it getting started. As you see, a wild 30S ribosome comes in searching for the Shine-Dalgarno sequence to start the process. Ah, there, this is special now. You see, the Shine-Dalgarno, which functions as a template to help line up the mRNA strand, has been found by our wild 30S ribosome. What's this? Folks, this is real special. IF1 has just entered and looks excited to bind to the A site. But not without IF2 coming in to steal the thunder. These initiation factors are truly, truly majestic. As you can see, IF2 has an amino acid group and uses GTP to add it to the P site of our small subunit. Ah! But now the 50S ribosome is coming in hot. But once added, IF2 runs off, having used up its GTP when helping the 50S ribosome bind to the mRNA. It leaves in search for yet another amino acid in its quest to complete a polypeptide chain. Oh, look there! An EF2 GTP. You know what that means. It's time for elongation. Observe, as the EF2 GTP settles into the A site carrying a new amino acid, the anticodon from the tRNA starts to mingle with the codon from the mRNA. We wait to see if the two are a love match. Yes, the anticodon and codon are a match. EF2 is then allowed to hydrolyze GTP, dissociating from the ribosome, while the amino-acyl tRNA is invited to stay. We are now gearing up for transpeptidation, folks. During transpeptidation, the amino-acyl tRNA in the P site will gift the amino acid chain to the amino acid tRNA in the A site. And boom! EFG GTP pushes the tRNAs aside. The tRNA in the P site is pushed out of the ribosomal complex, and the amino-acyl tRNA with the amino acid chain is pushed from the A site to the P site. That, ladies and gentlemen, is translocation. The EFG GTP is hydrolyzed and released from the complex. Now we wait for another brave tRNA to add to the chain. This ribosome is just chugging its way through this mRNA strand and, oh, what's this? A stop codon. It's just butted its way right into that A site. Well, it looks like the end of this polypeptide, and that means certain destruction for the ribosome. Let's see how this unfolds. The release factor is coming in with water molecules. It just hydrolyzed that ester bond. That brand new protein is floating around now, everyone. Alright, it looks like RF3 is hydrolyzing that GTP, and it's making the RF1 and both subunits leave. Don't worry, the ribosome may have been disassociated, but it's going on to synthesize other proteins elsewhere in the cell. That protein doesn't really do much, doesn't make sense. What? Ah, that's why those chaperonins are folding the protein. What is it saying? That mistranslation is pretty apparent here, but it wasn't that bad. It says, "My man Mitch." Ladies and gentlemen, you just watched a very complex process. And look, we have a functional protein from RNA. Isn't that amazing? Thanks for coming with me on this adventure. Until next time.